voted for the 5th of March. Please, if you didn't vote already, please try to do it. You can also do it right in the lecture now. So log in to Moodle, please, and check the box when you want to have the date, so that I can send out the email this week or next week when the final day for the exam is scheduled. So that was the first announcement. The second announcement is, please keep in mind that this lecture will be evaluated during the semester. So usually it's mid of December when the TUM survey is sent around, and everybody of you is asked to evaluate the lectures and give grades and announce what is not so good in the lecture and what is good. And yeah, so please participate in this. It's totally anonymous, so I won't see your name. And if you have to any critics or anything, please let me know via this evaluation. Okay, today we have to hurry up a little bit because we have a lot of stuff we want to finish today. Please keep in mind, next week there will be the guest lecture by Professor Schmidt on ionosphere modeling from space geodetic observations. Since the ionosphere is one part, so the loaded part of the atmosphere, and this is also somehow important for Earth observations and geodesy, since mostly the microwave signals are delayed when they propagate through the ionosphere, and if we do not take into account this kind of perturbations or signal errors, we won't be able to interpret anything we measure with Earth observing satellites. So this will be a nice excursus. It's also part of the exam, so only because it's a guest lecture doesn't mean that it's not important. So please be there next week, and then we can start with today's topic. So we want to have a closer look on Earth rotation, how the different formulas are derived, and how we can use the final equation we will obtain today in terms of reliably interpreting the Earth system. First, what did we learn last lecture? So we have the transformation from the inertial system into the Earth-fixed system, or from the Earth-fixed into the inertial system, by doing or performing 3 different rotations. Yeah, the rotation matrix W, then the rotation matrix R, and the rotation matrix Q. W describes the motion of the celestial intermediate pole in the terrestrial system, so the mean Earth rotation axis or the instantaneous Earth rotation axis, as seen when you are placed on the Earth crust. Then we have the R matrix here, which describes mostly the rotation around the rotation axis itself, which means the diurnal rotation of the Earth. And then we have the matrix Q, which describes the position of the celestial intermediate pole in the celestial system, so as seen from space. And so we have these 3 different rotations, and they can be expressed by 5 different angles. So we have small xy in the green matrix, the gust or Earth rotation angle in the middle R matrix, and in the matrix Q we have the capital X and Y, which describes the precession at nutation. The precession at nutation is the change of the direction of the Earth rotation vector in the Earth-fixed and the space-fixed system. It's caused by the lunisolar gravitational torques, so the gravitational pull of the Sun excites the precession motion, whereas the not coin or the deflection of the barycenter of the coupled Earth-Moon system is causing the nutation variations. It's known for centuries from astronomical observations, but is really regular and well predictable. In contrast to this, we have the Earth rotation angle, which is related to the universal time, and it shows irregularities in the Earth's angular velocity due to any geodynamic processes. So we will learn cause or excite changes or variations in the length, and parameter to measure this is the so-called LOD, the length of day variable. This is a really irregular and not easy to predict variable, and that's why we learn something about this motion, or that's why we can determine this motion only by space geodetic observations like VLBI, where we can really precisely monitor this parameter. And finally, we have the polar motion, which is the green matrix here. It is the change of the direction of the Earth rotation vector in the Earth-fixed system in contrast to the Q matrix. It's like the angular velocity, really hard to predict and follows a really irregular behavior. So this is also, or can also be only monitored by space geodetic observations. So we have 2 out of, or we have more or less 3 out of 5 parameters which cannot be handled via models. So this is why we have to use observations in order to reliably estimate such time series and provide them for the user. That's something space geodesy or the geodetic disciplines are doing. We have the IERS, which is the International Earth Rotation and Reference System Service. We learned already that this service, it's an official service, provides the terrestrial reference frame, so the Earth-fixed coordinate system, in order to express changes or dynamics of the Earth system in this reference frame. And moreover, as the name is stating, this service is also responsible for the Earth's rotation, and that's why this service provides a time series of all these 5 parameters regularly on a daily basis, let's say, for the user. Okay, that's what we learned last lecture. We have here the relationship between geophysical fluids and polar motion. We will come back to this later on in the lecture today. And now we want to really directly derive the physical model of the Earth's rotation. So really it's an equation which we can use in order to relate geodynamic processes to variations we observe in the Earth's rotation. And in order to start this, we can state that or assume that the rotational motion of the Earth is totally comparable to that of a physical gyroscope. And if we understand the gyroscope, the behavior of the rotation of the gyroscope, we also understand or can use these equations in order to understand the rotation of the Earth. We already started with this derivation, so we will go through this 7-step procedure, starting from the rotational motion of one individual mass element, how this is physically described, and end up with the rotation of the Earth within the Earth system. And in between, we have to deal with a couple of assumptions. First, we have to extend a single mass element into a system of mass elements. Afterwards, we consider the non-rotating reference system, so the rotation of the Earth as seen from space, from the inertial system. Then we look how this would look like when we study the Earth rotation from a rotating reference system. So we end up with the rotating solid body, and afterwards we introduce deformations and variations in the subsystems of the Earth, like the ocean, the atmosphere, hydrology, and so on, in order to finally end up with the Earth rotation equation. I can say this for sure, that this equation is very important. So keep this as a note, so please try to understand the following slides today, because this is for sure something we will face maybe at the very end of the lecture. Again. Okay, so let's start. The rotational motion is described with respect to a non-rotating reference system. And in order to describe this, we first have to formulate the angular momentum capital H of a rotating mass element. We already heard this, that the angular momentum is the product of the mass of this element times the cross product of the position and the velocity vector. And if we reformulate this equation, we can say that the track speed, which is this v here, is the cross product of the Now, angular velocity cross the position vector. If we insert this equation into this equation and rearrange the formula, we end up with this special formula here, so where the angular momentum is related to the Earth angular velocity by this factor m to m times r squared. The unit of the angular momentum is kilogram per meter squared divided by seconds. And so this is everything we know already. And the momentum of inertia, so this prefactor here, the scaling factor, can be abbreviated or substituted with the moment of inertia, capital J. And this, if we insert this here, we end up with h is j times omega. So we see that omega and h are directly proportional, and that the proportionality constant is the moment of inertia, so the product of the factor which is right in front of the omega. The direction of the angular momentum is not constant, and it depends on the direction of the track speed. So that was the right-hand rule. If we have the position vector with the pointing finger, the track speed with the middle finger, then the thumb is showing is giving the direction of the angular momentum. So capital H vector. This won't work with the left hand, so that's why it's called the right-hand rule. And you see if the track speed, the velocity of the track speed is changing, then also the angular momentum, the direction of the angular momentum is changing to the opposite direction. Okay, without external forces, the angular momentum is a conserved quantity, which means it's constant. Yeah? So there's no loss of rotational speed, no loss of energy. Within this system, everything is constant if we don't assume external forces. If the distance of the mass element to the axis of rotation decreases, the angular velocity has to increase accordingly due to this formulation here. So you see if r is changing, then for sure the mass cannot change. That's why omega has to change in this equation. Yeah? And that's really easy. The smaller r is, the larger must be omega, and vice versa. The larger the distance from the mass element to the rotation axis is, the smaller this omega has to be. So there's this prominent example with the figure skater. So you see if the hands are far away from the rotation axis, then we have a smaller angular velocity t, whereas when the hands on the mass elements are closer to the rotation axis, then the omega, the angular velocity is increasing. And the same holds with the Earth. That was, I think, the final question I asked last time. The LOD parameter shows the length of day, and we learned that this length of day is getting smaller currently. No, other way around. So what's happening currently in the Earth system? We faced this one of the last lectures. So the keywords are here: post-glacial rebound, or GIA, glacial isostatic adjustment. So the Earth's figure is expanding a little bit, especially in the Scandinavian and Greenland region due to the ice mass loss. The crust is now doing this rebounding effect, so it's getting far away from the rotation axis, which means, in fact, if you compare this to the figure skater, the Earth's velocity is, the Earth's angular velocity is slowing down. And we learned that the mean value of this LOD time series was something at plus 1.7 milliseconds. So more or less the total duration of one rotation is 24 hours and 1.7 milliseconds. And this is exactly caused by this behavior.
Is increasing water vapors in the atmosphere has a big enough mass to have this effect?
Could be. We will face this at the very end, where we study the different relationships and phenomena related to the Earth rotation. There you will clearly see some geophysical processes due to mass relocations affect the Earth rotation. Okay, so this was now one single mass element. If we extend this to a rigid system of point masses, so now we assume the Earth is not one point, but we have a system of point masses somehow defined, then we can extend this equation simply by inserting the sum over the n mass, n point masses. So we have now an individual position vector, we have an individual track speed, and we have an individual mass. Can you say or explain me why we have an individual track speed? Because it should be common to all the point masses, so that all point masses are rotating with the same velocity around the rotation axis. Is that true?
It's only true if we assume the Earth is rigid.
Sorry?
It's only true if we assume that the Earth is rigid body.
Yes, it depends, but as you see, it has to be constant here, so they do not have the same track speed, because, for example, point masses at the equator are more away or far away from the rotation axis, so they are rotating slower compared to point masses right next to the pole. So the rotation here is always a function or related to the distance of the point mass from the rotation axis, as we had before. If we now substitute this again, we have here you see the relationship between the track speed and the distance or the position vector of the individual mass element. If we substitute this by this, we can extract the location dependency out of this velocity, and we end up with this equation again, where we have mi/ri squared times the angular velocity, which is now constant for all the different point masses. If we now again replace mr squared with the moment of inertia j, as it was done in the equation before, then we cannot replace this with this constant j, but with the tensor of inertia. So the moment of inertia j was this product for only one mass element. If we have now the rigid system of mass elements, we have to extend this by the tensor of inertia. So mi/ri squared is replaced by this capital I, and the capital I looks like this. It's a 3 times 3 rotation matrix together with the mi here in front, and you see that we have some elements on the major axis, and the off diagonals are also represented here by products of the different constituents. It's a symmetric matrix, and the tensor of inertia, so this matrix describes the distribution of mass elements within the Earth system. So we will see this in a couple of slides, that this tensor of inertia gives us a picture, time-dependent picture of the Earth, of the mass redistribution within the Earth system. Yeah? So if we have any mass redistributions in the Earth system, somehow this will affect the different elements of this matrix. Okay, if we move on now, in a closed system, the total angular momentum is conserved, which means it's constant over time. And if something is constant over time, the first derivative of this quantity with respect to time is 0. Yeah? So that is something shown here. And now something which is not in the script. This. We have here a nice overview then. If you build up this table. And look first for the external forces. And we have reference. There's another contribution. And finally, the deformable Earth body. Something like this. Then we ended up now with the first step of our derivation, where we say the change of the angular momentum with respect to time is equal to 0. That means that we do not consider, as is stated there, no external forces. we do not account for any rotating reference, and we do not take into account deformations, which means we assume a rigid earth body. So if we neglect all of these three effects, we end up with exactly this equation here. So the angular momentum, the total angular momentum is a conserved quantity, which means the sum of all the different I angular momentums are constant. And now we start extending this equation by introducing external forces. We for sure have external forces, gravitational forces due to the sun and the moon, due to extraterrestrial planets or any other things. So this for sure is not constant. We have on the left hand or on the right hand side of the equation, we have something different than 0. And if we now look at this equation again, dh, so the angular momentum derived after the quantity t, then we can use this equation here, and m is constant, so we have to derive the cross product here, and this is the chain rule of the cross rule of the derivation. So the derivation of Ri cross Vi is the derivation of the first quantity cross the second, plus the first quantity cross the derivation of the second quantity. So as it is shown here, so and then we are now in a rigid system of point masses, which means that the r after dt is 0, since we have no variation of the position vector. Yeah? So this is 0, which means the first cross product is 0, and we only have to deal with the second cross product, and the temporal derivation of the velocity is equal to the acceleration. That's really easy, everything like this here. So we end up with this equation, and if we now insert this m again into the cross product, we can decide if we want to multiply the first quantity within the cross product or the second, and if we multiply the second product with this, accelerations times masses or times the mass is always something like a force. Yeah? It's always a force. So we have, and finally this equation here, where the temporal variation of the angular momentum is equal to the sum of the cross product of each individual mass element across the force acting on this mass element. And this is equal now to capital L, which means that the variation, temporal variation, with respect to time of the angular momentum is equal to capital A, and L in this equation means the total external torque. Yeah? So the gravitational acceleration or acceleration caused by the sun, moon, and other planets. So we have here this equation, which means that the external torque L and the angular momentum, the total angular momentum, are balanced to a certain extent. And this is already the second quantity. So our derivative after the time is not equal to 0, but equal to the external torques L. And this means, in fact, we now account for external torques. We still do not account for the rotating reference, and for sure we are still in the rigid system, which means the change from the first row to the second row is simply caused by this introduction of the external torques in this case. Okay, now let's extend the equation by the rotating reference system. If we have a rotary motion in a rotating reference system, for example, the terrestrial reference system, the Earth with respect to the Sun in the ICRF, we have for every arbitrary vector r, in this case, again, this equation. And now, the coordinate axes do not participate in this rotation. Yeah? So therefore, the unity vectors of our coordinate system are E1, E2, E3, and the derivatives after the time are 0, since they are constant in time. They are non-rotating. Which means, in fact, we have the ICRF coordinate system somewhere dislocated from the Earth. Yeah? This is non-rotating, this is invariant in time, and we have our system of the mass elements, so the Earth, which are rotating. But now we assume that the reference system is rotating, for example, satellite coordinates within the ITRF, as seen from the ITRF, then the ITRF is a co-rotating system with the Earth, yeah? So this reference system is now rotating, which means we have to deal or handle somehow our variations, temporal variations of the unity vectors of the ITRS system, and they, since they co-rotate with the Earth, can be simply expressed like this. So Ej dot is equal to the cross product of the angular velocity of the Earth cross the unity vectors of the coordinate systems Ej, and J is equal to 1, 2, 3. And this means now for any arbitrary vector in this reference, in the rotating reference system now, we get this equation again, and our dr after dt is not constant over time anymore. Yeah? So we have to introduce now variations of the position vectors, since the position vectors change with respect to time. And this is done like this. We have again here r dot j times ej plus rj times e dot j. So as we had it before, the temporal derivative after the cross product in this case. Now we have the first quantity here, and for the second quantity, for this ej dot, we can insert this equation here, omega cross ej, and we end up with this equation. Yeah? So we insert this here, can rearrange this, so extract the, forward this rj into this cross product, so it's ended like here. So we have this equation, and this equation is again the temporal derivative after the time here, plus this cross product at the end of the equation system. Yeah. So is this clear how this is derived here? So the total derivative of the position vector with respect to the time is the partial derivative, as we have it here. The partial derivative of r with respect to time plus this omega cross r cross product at the end of this equation. And now we end up with the next step. So we have now the balance of the angular momentum in the rotating reference system can be expressed like this. So now we have again our dh after dt, or divided by dt here, is equal to the partial derivative plus omega cross capital H is equal to n. So this is dh after dt, then we end up with equal to L. And now we have to account for this first part here, where we assume that this is 0, but this isn't 0 now, which means then that we have a quantity for this, which is equal to this, and this can be then inserted and lead to this equation. And this equation is then the next row. Oh, I did it somehow. Because it's getting a little bit crowded on the left hand side now. So we have the next row then. Where we have dh after dt is equal to the partial derivative plus omega cross capital H, and this is equal to the rotation of torques. Let's do like this. So now what did we do? We account for external torques, since we set the right hand side of the equation equal to L. We now account for the rotating reference in this case, so this is also already accounted for, but still we are in the rigid system. And for sure, as you can imagine, there's only one row left when we introduce the next two physical phenomena in this case. Okay, so we now have everything. The balance of the angular momentum in the rotating reference system, this equation from the slide before. The angular momentum of the rotating solid body is equal to this. Capital H is equal to I, the tensor of inertia, times the times the angular velocity of all the mass elements. We can take an assumption now that the coordinate axes are principal axes. So, principal axis, which means as a consequence that I has a diagonal structure. So this I in a really simplification can be seen as this. We have A, B, and C on the main diagonal, which are the principal moments of inertia, and the off diagonals are 0 in this case. Yeah? And for sure, these ABC quantities describe the more or less the lengths, the location and the lengths of the x-axis, the y-axis, and the z-axis. And you see for sure that due to the that the Earth is a deformed sphere, let's say, the A and B quantity are nearly equal. Yeah, since we have a rotational, more or less rotational symmetry in the equatorial plane. But for sure, in this case, C is much larger as seen in this equation. So the tensor of inertia comprises only main diagonal elements if we assume this rotational symmetry figures. And now we can still extend the equation, because now we can introduce the vectors itself. So omega comprises of 3 elements, since we are in a three-dimensional space, and also the quantity L, the vector of the external torques, is a 3-dimensional vector. And if we insert this in the equations, we end up with this equation that the partial derivative after the angular momentum at any point t with respect to t is equal to this if we substitute the capital H with I omega in this case, and this is then exactly equal to ABC times omega 1 to 3 dot. And therein, or with this, using this relationship here, we can derive the so-called equation of motions. Equations of motion for the rotation of a rigid body in the principal coordinate system. On the left-hand side now, we have the external torques L1, 2, 3. And on the right-hand side, we have this system of equations here. And these equations are the so-called Euler's equations of motion. So already published by Leonhard Euler, born in 1765. So here you see the really famous publication of him, where you see that these quantities here, CC minus BB divided by A, are somehow directly related to these motions. That's why these motions here are called the Euler equation of motions. And this is then something we have here, that this is are the so-called Euler equations. So now we can use these equations in order to introduce the last phenomena we want to account for in our rotation theory. If we now extend the rotating rigid body to a rotating deformable body, so introduce the Earth dynamics, the deformations of the Earth body, then we have again this equation, so the Euler equation, and the angular momentum is equal to this, where we have the tensor of inertia I times the rotation, the angular velocity omega. And for the rotational body, or for the deformable body, we substitute now this equation here or we extend this equation by the so-called small h quantities, the relative angular momentums. Yeah? So small h is now the relative angular momentum, and it's more or less the sum of over the n point masses we have. Again, mi times the position vector cross the relative angular momentum, so the relative track speed, let's say. And this describes the motion of the mass elements with respect to the reference system. So in this equation, the motion comes into the game, let's say. So if we have wind patterns or anything, so moving masses over the ocean, then these motions somehow affect these small h quantities here. And now we are nearly done. If we take this equation here, so the first one, the Euler equation, substitute the capital H by this equation taking into account the tensor of inertia, the angular velocity, and the relative angular momentums, and insert this here. So first we have to insert this equation here, which is this more or less, plus omega t cross, and here we have again this expression is equal to the external torques. Then we end up with this equation, and this is the famous and really important Euler-Liouville equation. So please, since I made the mistake here, we have the Euler-Liouville equation. I cannot write it since the space is not enough. T is equal to yeah. And now what did we do? We take into account the external forces, the rotating reference, and the deformable Earth body, and this leads us to the so-called Euler equation. So this is really important now, this equation. And within this equation, we have something, maybe it's written on the next slide. Yeah. So this is a really important equation, and that's the fundamental equation in order to relate Earth rotation variations in the Earth rotation to geodynamic processes. Since we can use this equation in order to account for two different types of effects. First of all, we have the tensor of inertia, times the angular velocity, and the tensor of inertia describes the distribution of the mass elements, as we said before. It's a time-dependent variable, so that's why we have the t in brackets. And this is the so-called mass term, so because it describes changes, or it relates variations in the Earth rotation to variations in the mass distribution, so it relates variations in the Earth rotation to mass redistributions within the Earth system. If we have a mass placed somewhere on the Earth, and then take this mass and put it somewhere else on the Earth, yeah, it's a mass transport, then somehow this equation is affected and the Earth rotation is affected. And on the other side, we have these small h quantities here, which are related to the relative angular momentum, and this is called the motion term. So if we have moving masses on the Earth, then this motion, or these masses have a kinematic energy, and this is somehow affecting the Earth rotation. Yeah? The Earth rotation in this equation here is hidden or is comprised within this omega vector. So on three parts here, on three places within this equation, we have the Earth rotation vector of the Earth involved. So this is a really important equation, please keep it in mind. If we now look a little bit closer and study a little bit how this equation varies, we can distinguish between the two different processes I introduced before. So if we have displacement of masses, which means a temporal change in the tensor of inertia, then, for example, this happens if a mass is redistributed or relocated within the Earth system. Yeah? And this is then, for example, affecting this this capital I here, which somehow affects the whole equation. On this other side, we have the so-called motion of mass elements. So if a mass element is moving, like for example an ocean current or a wind current which transport masses, then the motion term is affecting the relative angular momentums, the small h quantities in this equation. So you see the time-dependent equation, or the time-dependent quantities due to these mass motions and mass relocations are I in this case, and the small h in this case. Yeah? If we look closer, how is I? How can I be rewritten then? We have for a rigid system and equatorial symmetry more or less, we had the equation with an A, B, and C on the main diagonal, and the off diagonals had been 0. Now we have, if we want to account for mass redistributions, we can insert here small quantities like these C quantities here. And for the relative angular momentum vector, we insert this H1 to 3 in this equation. And this brings us then to the summary, where we have all the different compartments written again. So we have model approaches for Earth rotation are based on the balance of angular momentum in an Earth fixed coordinate system, which means a co-rotating coordinate system, and this leads to the Euler-Liouville equation. This is the Euler equation, yeah, as we have here. If we extend the Euler equation by this special formulation of the angular momentum, where we have the mass term and the motion term in both, then we end up with the Euler-Liouville equation. And here the quantities are given again. And the tensor of inertia, as it was shown before, was of this shape. And this is more or less the tensor of inertia, an approximate tensor of the Earth, which is time invariant. So this I0 plus a delta I. This I0 are more or less the principal moments of inertia A, B, and C, and all the variations or all the elements of the tensor of inertia which are describing mass redistributions within the Earth system are then comprised in this time-dependent tensor of inertia here at the end, this delta I at the end of this equation. Again, here it's written this is I0 plus these small elements we introduced before, which reflects the mass redistributions. Again, the relative angular momentum here, the motion of the mass elements, where we have this point mass specific relative velocity for each different mass element. The omega vector in this case comprises a capital omega times this. These quantities here, we named it M1, M2, and 1 plus M3. M1 and M2, so the first two elements of the Earth rotation vector, are the so-called, or they can be related to the polar motion. So the dislocation of the instantaneous rotation axis with respect to the conventional intermediate pole, as seen from the Earth fixed reference system. The third row here is 1 plus M3, which is more or less the angular velocity, and N3 is here this delta ut1 or LOD. That's why it's written 1 plus, because for sure we have, on one day we have one rotation of the Earth around itself, which is the capital omega, and then we have a small quantity, omega times M3, which is LOD, so the deviation of one rotation from 24 hours. Okay, if we look again on the equation, this is the Euler-Liouville equation. We know the capital I here, which comprises this formulation, I0 plus delta I. Main diagonal, the principal moments of inertia, A, B, and C. Off diagonals are these small elements here, abbreviated with C something in the subscript. Then we have the Earth rotation vector, which is M1, M2, 1 plus M3 times omega. We have the external torques, L1 to 3, and we have the relative angular momentums, H1 to 3. So more or less everything in this quantity can be is expressed now, or is formulated now. We know everything: gravitational torques, relative angular momentum, the motion term, we have the mass term, and we have the Earth rotation vector. And now what is finally missing is we have to relate this equation to the Earth rotation. So what we want to do is now we want to reformulate this equation by putting omega on the left-hand side of the equation and all the rest on the right-hand side. Because then we can use this equation in order to study, observe changes in the omega vector, which are changes in the Earth rotation vector, and relate them to anything happening on the right-hand side of the equation. So what we have to do is we have to solve this expanded Euler-Liouville equation for the Earth rotation vector. Yeah? So rearranging this equation and solving for omega, which means omega must be placed on one side of the equation, the rest on the other side. If we do this, we have to take two key assumptions in order to simplify this, because it's not so easy. First of all, we have to assume a rotational symmetry of the Earth around the z-axis, which means that A is equal to B. Yeah? So this equation here, A is equal to B now, which means that we have a rotational symmetry at the equator. We only have the Earth's oblateness left, that A and B differ from the C quantity here. And secondly, products of small quantities, so the Cij, this Hi, and this Mi, and the temporal derivatives, so C dot, H dot, and M dot, are negligible. So the products of small quantities are too small to be accounted for, so we neglect them. Which means, in fact, in this equation, here, for example, we have I times omega, so we would have an element in this resulting vector, which is A plus C11 times M1, and the C11 times M1 is neglected. So we end up with these equations more or less. Yeah? If we then try to put all the M quantities on the left-hand side and all the rest on the right-hand side. This is how you solve for the Earth rotation vector. Yeah? And this is now the final resulting equation system. Components of the Earth rotation vector as functions, so the components of the Earth rotation vector here on the left-hand side, as functions of external torques on the right-hand side, because we have this L1, L2 here. Functions of mass redistributions, since we have these elements small c here, which are elements of the tensor of inertia, so mass redistributions within the Earth system, and functions of mass motion, since we have these small h quantities here, and they are, or variations in these small quantities are caused by dynamic processes in the Earth system. The right-hand side of this equation system is called the so-called excitation functions, because variations on this side of the equation excite variations in the Earth rotation. We will face this afterwards again. So that are excitation functions which excite the Earth rotation. And if we simplify the left-hand side again, so we have this specific quantity here, A divided by omega times C minus A, which is more or less a constant. This is then 1 over sigma r, and sigma r being the Euler frequency here in this case, which have a period of 304 days. Euler frequency, it's named because we assume, or in this case, since these are time invariant parts, constant parts, that they account for a non-deformable body. So here we do not have any deformations of the Earth body involved. All the deformations in the Earth body are concentrated on the right-hand side of the equation system, as it is shown here. Okay, let's simplify it a little bit in order to study or do a couple of examples. First of all, we do assume no variations of the tensor, which means the mass is, or we do not account for, we do not have, in our example, mass redistributions, yeah? No mass transports at all. We have no relative angular momentums, so the small h quantities are 0, which means we do not have winds, we don't have currents, so everything is more or less rigid. Yeah? We are on the rigid body again, and we have external torques. So we end up with this here. Now no external forces and no deformable body, only the rotating reference system. If we do this, so if we cancel out all the small c's, all the small h's, and the products, we end up with this equation system, where we have m1, 2, 3 dot, here with a prefactor plus m2 or minus m1 is equal to 0. So the right-hand side totally vanishes. Yeah? What does this mean? Excitation functions are all equal to 0. Yeah? If we do not have any torques or variations in the tensor of relative angular momentum, excitation functions are 0, which means we do not have any LOD variations, since n3 is related to the length of day. So we have a constant rotation rate of the Earth. with an Euler period of 304 days. And we have here no variations of the no, only small variations of the polar motion with a period of 304 days. If you look this, that's exactly the case here. We have the figure axis, which is the rotation axis, and then the figure axis. Then we have the rotation axis, where we have an angular velocity of omega, and due to the dislocation within the rigid body, we have excited this Euler period of 304 days. If we are in a non-rigid Earth body, this 304 days change to the so-called Chandler period of 434 days. And this free polar motion is superposed then by a forced polar motion. Yeah? Not so important here, only take home message here is in a rigid body we have the Euler period excited of 304 days, and with in a deforming Earth body we have the Chandler period of 434 days excited. If the figure axis do not coincide with the rotation axis, as it is the case, the rotation axis performs a free oscillation with respect to the Earth's fixed reference frame. That's what we had already last lecture. If it's a three-dimensional plot, x and y are the polar motion components. Yeah? The motion of the tip in the terrestrial system, and on the z-axis you have the time, and then you see that this rotation is mainly a superposition of two oscillations, a 360-day annual oscillation and this Chandler oscillation, since we are on a deformable Earth body. If you look on the two-dimensional case here shown, on the one-dimensional case, no, from the three to the two-dimensional case here shown for the x component, so only the variation in this direction here. Yeah, then it looks like this. Again here in blue, plus minus 0.4 arc seconds here, and this oscillation mainly is a superposition of the annual oscillation and this Chandler oscillation due to the dislocation of the rotation axis from the Earth's figure axis. And now we come to the last slide of this part. Now the real case, various dynamic processes in the Earth system influence the Earth rotation. We have the balance of the angular momentum, so the Euler-Liouville equation in the middle. And now we can study if we have, for example, variations in the ocean. Yeah? If an ocean model, for example, gives us variations in the mass term, so if mass is transported from A to B or relocated from A to B, or if we have large ocean currents like the Gulf Stream or the Great Conveyor Belt, which we will face in one of the last lectures where we will talk about ocean models, then delta I and small h are affected by these mass redistributions and motions, which in fact change the Euler-Liouville equation. And if we use these equations here and insert delta I, so the small c quantities or the relative angular momentum h here, we can study the impact or quantify the impact of this subcomponent of the Earth system on the Earth rotation. Yeah? So the trick is that we use these equations here and try to find or try to fill in these small quantities here, C, H, and L, based on any other subcomponent variations, for example, ocean variations derived from an ocean model. Because, for example, we can use an ocean current model in order to model these small h quantities and then study the impact on the Earth's rotation. This is how we can try to relate all the different geophysical quantities to the Earth's rotation variations we observe. Since the left-hand side of the equation system, so the Earth rotation variations or variance of the Earth rotation vector can be observed with the geodetic space techniques, whereas the other side, the excitation functions, can be derived from external geophysical models we have. Yeah? We can do this for the ocean, for the atmosphere, for the hydrology, for example. We only account for mass redistributions because we take not into account the flow velocity of the river, because this is something you cannot really model because it depends on so many we can, for example, account for a mass redistribution due to hydrology. The tides due to sun and moon are causing variations in the Earth's rotation, and here also the external torques L are affected. We have loading deformations, so the crustal rebound, the post-glacial uplift is, for example, relocating mass elements within the Earth system. We have the rotational deformation, which is also relocation of mass elements, or we have core mantle effects, which also affects the H and the delta I quantity. And how these things are affected, we will learn when we talk about, for example, atmosphere models, ocean models, or in the next couple of slides. Yeah. That's so far with this chapter. Any questions?
What about those three dots? So these are.
Yeah. In this case, for example, we have volcanic eruptions, which abruptly relocate mass elements from the Earth's interior to the atmosphere. If you have gigatons of ashes, for example, located or relocated into the atmosphere. Also earthquakes, where we saw, for example, this example of the Chile earthquake. There, the Santiago region was relocated by 3 meters, really abruptly, and this is changing something here or affecting something here. So there are a multitude of effects, even effects we don't know, yeah, are somehow within the system. We also, since this is not a complete picture, for example, the cryosphere is missing. If we have relocations of mass due to snow melting or motions of large glaciers, for example, or ice fields within the ocean, and this also comprising. Also the biosphere is affecting the Earth's rotation. Anthroposphere, for example, if the human beings do cause relocations of mass elements, and so on and so on. So there are a multitude of effects or subcomponents hidden in the 3 dots. Because here we account for atmosphere, ocean, hydrology, more or less a little bit solid Earth here. We have the Earth's interior a little bit represented, but yeah, it's not a complete picture. Yep.
Does the big amount of CO2 that we found in the atmosphere make any difference? Because we always speak about tons of CO2.
Yeah.
They were before on the ground, like oil and gas, and suddenly they're like.
Yeah, good question, but this is something not clear, let's say. The models are not accurate enough in order to account, because it's a rather small effect, let's say, because we talk about tons of CO2 emitted into the atmosphere, but I don't know if there exists a study which already relates the Earth's rotation velocity to the. It could be, yeah. But always imagine that we have an observation accuracy for LOD of 20 microseconds. So the left-hand side of the equation system, where we have the Earth's rotation vector compartments, can be measured with only 20 microseconds or 0.1 millisecond accuracy, and it could be that these variations are too small still that we can measure them. But theoretically, you can use such an equation and study the relocation and how this would affect, so you can quantify the effect of this relocation into the, with respect to the Earth's rotation. Sure, it's possible. Okay, so we switch not really the topic, but we extend our topic now a little bit to the next lecture, which is the lecture actually I wanted to give today, because it deals with the geodetic parameters as integral quantities, and we right away start again with the Earth's rotation. In this chapter, the Earth's rotation parameters are a subset of the Earth's orientation parameters. Earth's orientation parameters had been 5 quantities, or small x, y, the Earth rotation angle, and capital XY. Capital XY are the precision and rotation parameters. We learned that they are well predictable and can be modeled really accurately. That's why we skip them. And since we skip them, or since we have accurate models to account for them, we only have to deal with these three irregular quantities, the Earth rotation angle and the small xy parameters. And these three parameters are the so-called Earth rotation parameters, so a subset of these Earth orientation parameters. Variations are caused by a multitude of superposed effects. We have learned gravitational effects cause variations, dynamic processes in the Earth system, involving the redistribution and transport of masses within the system. The Earth's rotation parameters provide an important information on the balance of the angular momentum. So the angular momentum and external torques must always be balanced. But the time series do not allow for conclusions with respect to specific underlying processes without further knowledge. So we cannot simply take an ocean model, compute the effect on the Earth's rotation, and say this is the effect of the ocean on the Earth's rotation, because we have correlation and coupling mechanisms in between the different subcomponents. And that's why the interpretation and separation of these observed variations requires an independent information from numerical model approaches. That's what we will learn a little bit today. So what kind of information is required in order to model Earth rotation parameters? First of all, we have to know the distribution and motion of mass elements and various components of the Earth system. So atmosphere, ocean, hydrosphere, cryosphere, solid Earth, and so on and so on. And these variations of mass elements, distribution and motion of mass elements cause variations in the Earth's tensor of inertia, the relative angular momentum, and pressure-related loading effects. Yeah? That's also something we had on the slide before. The loading is also causing a redistribution of mass elements, and yeah. Moreover, we have to take into account ephemerance of the sun and the moon, since we have to account for external torques, and we have to account for tidal effects due to the gravitational pull of these celestial bodies. So here you see already a multitude of effects. We have a direct effect of a gravitational torque on the Earth rotation, plus the indirect effect via the tidal variations on the Earth's More or less, we have to take into account geometrical, physical, and biological parameters of the Earth, like the Earth's ellipsoid, the mean tensor of inertia, love numbers, which describe the density variations within the Earth's interior. So also here we have a couple of things to take into account, and all these results can be incorporated into an Earth rotation model, and the model results is highly depend on the completeness of the effects for sure, considered in this model, and the quality and consistency of the applied forcing. Moreover, model parameters are important. And this is a nice overview how this is realized. So Professor Seitz published in 2004 a very famous model called the Dynamic Earth Model, DIMEC, in the Geophysical Journal International article here. And what he found out, or what he tried to model, is on the one hand side we have geophysical processes like climate variations or weather phenomena, which are exciting changes or causing changes in the atmosphere, the ocean, the continental hydrosphere, or also the solid Earth. And these four subcomponents of the Earth system, so here we only account for atmosphere, ocean, hydrosphere, and solid Earth. For example, cryosphere is neglected in this case. Based on these four subcomponents, he computed mass redistributions and mass motions. Mass motions can be related to the relative angular momentum with small h quantities. Mass redistributions cause variations in the tensor of inertia. And these two quantities affect for sure the geometry, since we have, for example, the rebounding effect or whatever. They affect the gravity field, since mass is transported from point A to point B. and as we learned before, they all both affect Earth rotation variations. Then we have the gravitational forces of the sun and the moon, which are also causing atmospheric tides, oceanic tides, solid Earth tides, and to a certain extent also influence the continental hydrosphere. So also gravitational forces affect these, cause variations of the mass redistribution and the mass motion, and then affect the three pillars of geodesy. But in addition to this, the gravitational forces directly also affect the Earth's rotation via these extraterrestrial torques. And the Earth's rotation has a so-called back coupling to all these, to the solid Earth and the oceans via this rotational deformation. If the Earth's rotation is changing, for sure the centrifugal potential is changing, and that's why we have here a back coupling effect of the polar motion. When we move on from the rotating rigid body to the rotating deformable body, and somehow here the Chandler period or the Chandler oscillation is then caused due to the dislocation from the Earth's rotation axis to the figure axis. Yeah? So this is quite important. We have here direct effects which affect the three pillars. For sure we have relationships or correlations within the pillars, but we have also a gravitational direct excitation due to gravitational torques of the Earth's rotation and this back coupling. So three take-home messages here. We have direct effect on the one hand side. On the three pillars, we have a second effect here, a direct influence of the gravitational forces on the Earth's rotation, and we have the back coupling of the Earth's rotation on different subcomponents within the Earth's system. This is, as I said before, model results is highly dependent on the quality and consistency of the applied forcing and the completeness of the effects. Yeah, it is pretty sure that the rotational deformation also affects the atmosphere. Yeah, since the atmosphere is a co-rotating layer, let's say, of the Earth, so it co-rotates with the Earth. If the Earth's rotation is changing, also the centrifugal potential in the atmosphere must change. But this is something which is not yet understood, not yet modeled, or not yet accounted in geophysical model. That's why this arrow, for example, is missing. And that's the completeness of the model. That's a deficiency of this model, for example, that it doesn't account for this relation between the rotational deformation and the atmosphere. Okay, if we look a little bit closer on the rotational deformation, polar motion causes variations in the Earth's centrifugal potential, and the centrifugal potential causes redistributions of masses, in particular solid Earth and oceans. We end up with such an equation. It looks a little bit strange. On the left-hand side, again, you have the tensor of inertia elements, these small c quantities, time variant. And on the right-hand side, we have this strange expression here, r of k2 times m1, that's the quantity of the Earth rotation vector we already had, plus I of k2 times m2. Beta is only an abbreviation for a scaling factor, but important are these r and I quantity here. That is a complex number where we, the love number here, k2 is a complex number, where we have the real part and the imaginary part on the one hand side and on the other side. So we have the pole-tide love number k2, which comprises of these three quantities. It's a complex number with a real part and an imaginary part. And from the IRS conventions, for example, we learned that this quantity is 0.35 plus 0.0036 times I. Yeah? And these three different quantities here, which form the pole-tide love number, are responses of the solid Earth, where the density distribution of the Earth's interior is important. We have the response of the oceans, abbreviated here with this O, and we have mantle unelasticity. So when the mantle is not allowing this rebounding effect, for example, which is this delta K2 with this super, with the upper index A in this case. redistributions, as we learned, are coupled back into the Euler-Liouville equation via these two different subcomponents of the Earth system, the ocean and the solid Earth. So we have again this equation or this scheme here. If we cancel out everything now in order to study this, we will end up with something like this. We have a mass redistribution which is causing Earth rotation variations. The Earth rotation variation is causing a rotational deformation of the solid Earth and the ocean, and they are again affecting the redistribution of the Earth and then again affecting the Earth rotation. If we look at such a simulation, we have here the conventional terrestrial pole in the middle, and then this is this oscillation of the axis, of the rotation axis around. What we had in the three-dimensional plots before, and here shown now from as seen from above, let's say. Then we have the polar motion x and y component, and the rotation axis is performing this variation. You see, if you look at the simulation over 100 years, at the beginning, it's a simulation. You start with an oscillation between plus minus 1, and after 100 years, it's totally vanished. You say, why is it vanished? Somehow strange. We have the deformability of the Earth body within this graph here, because it's lengthening the period of the free rotation from 304 days to 432 days. That was 304 days, the Euler period, where the Earth is a rigid body. If the Earth is deformable, this period changes to 432 days. But more important is the next point, the consideration of the mantle unelasticity. This is simply due to the dissipation of energy caused by friction. Yeah? And that's why our polar motion is damped with time. Yeah? So we are not here in a friction-free world due to the Earth deformation and the consideration of this mantle unelasticity. This amplitude is damped, and over 100 years, polar motion would totally vanish. Yeah? So let's assume it's excited by something in 1900. So, and this 432-day oscillation then would vanish up to the year 2000. And without an excitation of this free polar motion, without excitation, the free polar motion would diminish within a few decades. As you see it here, after a couple of decades, the amplitude is really, really small, which means, in fact, that the figure axis is equal to the rotation axis after, let's say, 60, 70, or 100 years. But this is for sure not the case, since we know from observations, let's see if I find it again. Since we know from observation, with this three-dimensional clock where we have this oscillation of the Earth rotation axis with time, and this is for sure not vanishing. Since we see it in the observations, if we have a look again, here we have the K2 parameter again, and now we can model, since it is a complex number, we can have a look on the real part and the imaginary part. The real part of this number, is more or less related to the Chandler period. So in the conventions we have 0.3517, which is somewhere here. And if you look up what kind of Chandler period is excited, then we end up exactly with this 432 days. So the real part is related to the Chandler period, the length of the Chandler period, whereas the imaginary part is related to the damping of this polar motion. So what you see in the left and right hand side of this plot are two different imaginary parts. Here we have 0.002 and here we have 0.0045. And you see that the higher this number is, the imaginary part, the faster or the higher is this damping factor, which means the faster the polar motion is vanishing, and the Earth's rotation axis would coincide again with the Earth's figure axis. The envelope of this damping can be modeled with such an equation. That's now not so important. The only thing I want to emphasize here is this this quality factor. This is more or less an indicator for the stamping. You also see here that the quality factor is in this case 145, in this case 65. The smaller the damping factor, the higher is this, the smaller the quality factor, the higher is the stamping. And from the literature, a couple of attempts were made in order to estimate the stamping factor. What you see here are a couple of publications where we have this Chandler model period. So the Chandler period, you see that they quite agree within a couple of days, but the quality factor is really varying depending on the studies which are published in the geophysical journals. That's now not so important, only to give you a feeling that based on the observations done in the past and nowadays, we try to understand the key parameters of the Earth system, but we still end up with such uncertainties. For example, of the Chandler period here, a difference of 5 days, which is still simply due to the quality of the observed Earth rotation parameters or the background models not yet really good understood. So this is somehow still a result of the uncertainty of the models, of the incompleteness of the models we have so far. We have, for example, something which of the rotational deformation, which causes variations of the atmosphere, is totally neglected in this model, for example. Okay, numerical values for this delta I and this small h are derived from model data of the Earth system components. So let's now try to use an external model and study variations of the Earth rotation. So what can we use for such things? For example, we can use the global atmospheric reanalysis. It's called NCEP. NCEP is an atmosphere model, and this assimilates meteorological observational data and provides us angular momentums from wind fields and surface pressure variations. So now, for the first time, we try to combine space geodetic measurements with totally geophysical models. Yeah? So we take an atmosphere model, extract the wind fields and pressure variations, and derive angular momentum variations out of this. That are called atmospheric angular momentum. The same can be done with the ocean. For the ocean, we take a global ocean circulation model. In the last lectures, or after New Year's Eve, we will study them in more detail. What ECHO is a model, kind of model, or what NCEP is a model. But now, simply take home that ECHO is a global circulation model, ocean circulation model. It is somehow forced by NCEP, which means that it's coupled to the atmosphere. And here we use this model in order to derive oceanic angular momentum from currents and water mass transports. So we have the atmosphere model with NCEP, the ocean model with ECHO, hydrology is modeled with the global hydrological model LAD, which gives us information about water, groundwater, and snow fields from this model. And neglected in our example are now earthquakes, volcanoes, post-glacial uplift, or core mantle effects, and so on and so on. So we take these three subcomponents of the Earth system, of the complex Earth system, and look what we get. On the left-hand side, we have the X and Y components of the polar motion derived from these three different subcomponents, from the information of these three different subcomponents. So we computed this delta I and the small h quantities based on the three models, and computed our M1 and M2 quantity, using the Euler-Liouville equation. So this is more or less the M1 and M2 quantity on the left-hand side. On the right-hand side, CO4 means that this is a time series derived from geodetic space technical observations. So from VLDI together with GNSS and SLR. And if you look on the first stretch, okay, correlation 0.98, 0.99, they perfectly agree. The RMS difference, since we have here milliarc seconds, so 1 order of magnitude smaller, you see that, okay, we end up with 29 milliarc seconds RMS, so root mean square, so the scatter of the residuals, if you take the difference between both, of 29 milliarc seconds for x and 23 milliarc seconds for y. Is this okay, or what do you think? If I ask it this way, for sure it's not okay. It's not bad at the first glance. You see that they agree quite well to each other. So left in red, model data, right blue means observed data, observed parameters. So they quite agree, okay, but you see still 3 orders of magnitude worse than the accuracy of today's observation of polar motion. Because we learned with this geophysical fluids and polar motion scheme, I think it's the next slide, here, that the current measurement accuracy is somewhere here, 0.1 milliarc seconds, and the difference shows still a scatter of, let's say, 20 to 30 milliarc seconds. So you see 3 orders of magnitude worse than we can perform on the right-hand side currently. Yeah? So you see, in fact, that the models, the polar motion values derived from the models are still much too inaccurate compared to the observation accuracy we have nowadays. If we look at a longer time series here shown from 1950 to 2010, we can say, okay, if we look on the full polar motion, yeah, so our model results with respect to the observed quantity, unfortunately now it's red is the observations based on space geodetic data, and blue is the model here. We see we end up with a correlation of 0.95 and a really, really large RMS. Say, okay, do we understand something really not very good in this in the system? If we look on the Chandler period itself, which is based on the NZ echo, so the rotational deformation, which is due to the polar motion, then you see, okay, here we end up with a much higher correlation and a much smaller RMS. So the Chandler part is well understood, but we have other things, obviously, which are not well understood. So measurement accuracy is 0.1 milliarc seconds. You see all these effects above 0.1 milliarc seconds should be measurable, so should be seen in our time series, but we have here a couple of things which are still not detectable due to the measurement accuracy.
So we can measure it, but maybe the problem is with the model that we might not be able to model.
Exactly. The measurement accuracy is much higher than the model accuracy. So we have a measurement accuracy of 0.1 milliarc seconds, but the discrepancy between model and observations is around 20 to 30 milliarc seconds. So 3 orders of magnitude worse than what we can do with the observations. And if we look on the different compartments of the different effects, for example, in the LOD time series, remember today's observation accuracy is somewhere around 20 microseconds. This is the full LOD signal, yeah, here over the last 50 years. First of all, we have secular variations due to the core and mantle effects. We can account for them using models, so we can subtract this purple line from the blue line. So then we have the solid Earth tides, so tidal variations of the length of day. We have annual and semi-annual variations, and what we end up if we subtract these 3 magenta signals from the blue one is the measured time series, we end up with the green one. So this is everything we cannot explain up to now. Yeah, not by models from the atmosphere, the ocean, from this LAD, the hydrological model, and so on. These are the residuals which are left. You see that we are here at the level of an offset of 2 milliseconds and a variation, let's say plus minus 0.1 millisecond or 0.2 milliseconds, which is much larger than this 20 microseconds. And then we see special effects here in 1984 for example, or 1998. And if we look closer, what happens within the Earth system, then we see, okay, we have here the ENSO effects, ENSO, El Nino Southern Oscillation, which is a phenomena happening in the Pacific region, and this is somehow affecting the Earth rotation, not on a frequent matter, since the ENSO is caused only every couple of years, let's say every 3 to 5 years. We will learn this when we talk about the ocean models, but you see that we have still variations in the Earth rotation caused by the atmosphere and the oceans, which are known, but which we cannot project into the Earth rotation. That is a prominent example are these ENSO variations. Geophysical fluids and LOD, we learned that we have 20 microseconds measurement accuracy for LOD based on space geodetic observations. 20 microseconds are somewhere here. I would draw the line. And you see large earthquakes are totally not measurable with space geodetic observations, but all the other things are somehow contained in the time series. And now we can use the Euler-Liouville equation in order to explain, in order to minimize these residuals, because for example now we learned, okay, ENSO is causing a variation here. Let's try to find a model for the ENSO effect, subtract it, and then we end up with a much flatter residual, so we can take the next, or we can investigate the next geophysical process in order to finally perfectly explain the variations in the length of day, for example, based on external model data. Somehow it's quite impressive that we already moved on from the blue line here, observations. If we subtract all the model data, we end up with these residuals, so we can explain really a lot of the Earth rotation variation already based on atmospheric and oceanic models, but still there's room for improvement. Okay, final 2 slides. It's a kind of summary. The rotation of the Earth and its temporal variations are monitored by geodetic and astrometric observation systems since decades with a very high accuracy. And observations of the orientation of the Earth's axis and the angular velocity are transformed into a time series of Earth rotation parameters. So from the observational side, we get a time series of Earth rotation parameters for decades now. So VLBI started in 78, 79, so since more than 4 decades we have observations of the Earth rotation. A precise knowledge of the temporal variations is fundamental for the realization of the time systems, so universal time coordinated, or time systems on Earth, highly precise computation of geodetic reference frames. Yeah. Since we observe from the crust, we observed satellites orbiting in the inertial space, so we have to account for the Earth rotation. In order to relate Earth-fixed and space-fixed coordinate systems, and for precise navigation on Earth and in space. Earth rotation is really important. It's interesting for various disciplines in geosciences, since dynamic processes in the Earth are reflected in the temporal variations, as we learned before. We have a lot of things ongoing on within the Earth system which can be related to variations in the Earth's rotation. The Earth rotation parameters contain important information on geodynamic processes, since the ERP are directly related to the balance of angular momentum. Balance of angular momentum on the left-hand side, external torques on the right-hand side. Yeah? This equation must be balanced, so we are here. Angular momentum variations are linked to the motion and redistribution of masses. Yeah? So redistribution, mass relocations, but also motions like currents and wind fields and so on. And the interpretation of the observed time series can be advanced by geophysical models in order to separate the observations. And current research topics in this part are first the consideration of further system components in the simulations. So we have this DIMAC model which accounts for the atmosphere, the ocean, the solid Earth, and the hydrosphere. but for example not the cryosphere or biosphere or any other subcomponent. Prediction at various timescales of Earth rotation parameters. Inverse modeling and independent determination of mass transfers from other observations. We can also use the gravity field missions, since gravity field missions measure mass redistributions. This can be also somehow linked to the Earth rotation, but also satellite altimetry, because there we measure more or less the delta I. Yeah, so we measure relocations of point masses within the Earth system from altimetry measurements, and all this can be incorporated into this